Hi, I am Luke Oxley, a veteran of Team 6498, and in this presentation I will be discussing the FRC program structure based on our 2020 program. To give you an overview of this presentation, I'm going to be talking about the folders and classes involved in the program, as well as what a subsystem and a state machine is, and at the end I will talk about how we tuned our shooter for our 2020 robot. So to give you a basic outline of the folders in the program, the top folder is the source folder. This is what contains the entire program. Next in the orange we have the robot folder and the library folder. The library folder is what contains different kind of helper classes that we use to do various things, as well as drivers for kind of outside sensors that are not included in the WPI library. Now under the robot folder we have the subsystems folder. This is what contains all of the classes for the subsystems, such as like the drive subsystem, or depending on what mechanisms you have, the lift subsystem, the turret subsystem, stuff like that. Now the state machines folder contains what we call state machines, which are kind of a subsystem that contains many subsystems and combines them together. So say we have a shooter on our robot, we would have a shooter state machine that contains the flywheel subsystem, the turret subsystem, and the hood subsystem. I'll discuss this later on. Then we have the vision folder. This is what contains all the classes we need to connect and talk to the Limelight. A loops folder manages all of the looping and threading done in our program. So all of the subsystems usually run on their own thread. This loops folder kind of helps to handle that. Then we have our auto folder, and this contains all of the stuff that we need to run our auto program. First, I'm going to be talking about the classes contained in the robot folder alone. The main class for the entire program is called the robot.java class. And this is how kind of the driver station on the driver computer directly talks kind of back and forth. And you'll see in the robot.java class, it'll have different sections for whenever the robot initializes, or if you're running a teleop or an autonomous program. That's where all that is at. Next, we have our constants folder. This is probably the one you'll be updating the most. This contains all of our variables across the robot program, such as like port numbers for sensors and motor controllers, as well as dimensions of the robot. And the reason why we put all of our constants in one folder or one file is because it's very quick to change during like a competition setting. Then we have the control board class. This is how we convert the controller commands into robot commands. So whenever the driver presses like A, it'll shoot the ball or something. This is by having all of the controller commands in one class, it's very easy to change the button mappings to the driver's needs. Then we have the robot state class. This is kind of what contains all of the reference frames and translations between reference frames. And when I say a reference frame, I mean that, so on our 2020 robot, we had a turret mechanism. So different frames of reference are from like, if you're watching on the field, you'll see the robot moving around and rotating, or a frame of reference is from the robot itself, so that whenever the robot rotates, that reference frame rotates along with it. Or then you have the turret. The entire turret is rotating by itself along that. So you have different conversions you have to do to be able to convert all the way from a spectator looking on the field to the turret rotating around. And then also in robot state, we contain kind of what's going on with the game pieces inside the robot. So in 2020, we had 5 balls at a time. Inside the robot state class, we had information about where each ball was inside the robot at a time, so we can kind of track where they're all at. Next, we have the kinematics class. This contains forward and inverse kinematics for the drivetrain. And if you don't know what kinematics are, it's basically conversions for the position and rotation and velocity of the robot at a time. Next is the subsystem manager class. This contains functions that we want to apply to all the subsystems at once. So instead of having to go and call a function for each individual subsystem doing the same thing, this will do it all for us. This is also how we start and stop all of the subsystems at once whenever the robot is enabled or disabled. Next, I'll be talking about the classes inside the loops folder. First is the looper class. This is what actually creates the thread for each subsystem or whatever we're looping. And this also helps to prevent crashing. So by having each thing on a thread, if one of, like, say, our arm crashes, then we can continue driving and the program will still function even though our arm thread crashed. Then next we have the robot state estimator class. This is what kind of inputs observations into our robot state class. So it'll observe things such as like the chassis position or the turret position, and also their speed and direction as well. Also, if we have sensors, we can sense game piece updates as well and update where the robot thinks each game piece is at inside itself. Then we have the vision processor class, and this is what pulls vision data from the camera. It has a bunch of different commands for kind of converting from limelight information into coordinates of the object. Now I'm going to describe what's inside the auto folder and kind of how we go about doing our auto modes. First is the auto mode executor class. This is what actually creates a thread for the auto mode and executes it. And this is controlled by the robot.java class or the smart dashboard. So whenever the driver says, oh, I want to do the drive straight and shoot auto mode, this is where that command will go through. Then for our auto modes, we have different actions. So say we want to rotate the turret, shoot, or like follow a path with the drive base, we'll have a different action for that. And each action has kind of the same layout. It'll have the start method, an update method, is finished method, and a done method. So it's very easy to create your own action. And this is where in the auto folder, the actions are what actually interact with the subsystems and state machines of the robot program. Next, we have the modes folder. This is kind of what contains a list of actions that each auto mode will run. So say we want to have the robot drive forward and shoot. It'll have the drive forward action first, and then it'll shoot. So there's different ways to run an action. You can run an action in series, which is just sequential order. So if we want to drive and then shoot, we would have those two actions in series. Let's say we want to do them at the same time. There is a way to do parallel actions where we can drive and shoot at the same time. Now I'm going to go over the subsystem layouts. And there are two main versions of how we lay out our subsystems in the program. The first one is the simple layout. And this is for mechanisms that don't have many required actions. They kind of do the same thing over and over again. And if, say, this mechanism is reliant on another system, or it won't need many system states. So in this case, one of the simple layouts we had was the indexer on our robot. And this was just a wheel that spun until a sensor sensed the ball coming in. And that's all it did the whole time. So we didn't have to have a really fancy control algorithm for this. Now, if we have more complex devices, we would actually have a state machine. And this is where a device has many system states or positions that it has, or intermediary states required. So when I mean intermediary states, this is like a flywheel where you would say the driver is like, oh, I want to shoot. Well, the flywheel can't automatically go from not moving to up to speed. So you would have a spinning up state or an aiming state to where it would have to cross through multiple states to get to the final state. And by looking at the program, you'll kind of get a sense of what I mean when I say that. Now, the layouts for the simple subsystem structure and the state machine subsystem structure both have the same kind of base things that they all have in common. So the first thing is they have a constructor. This is where we initialize the variables used in the subsystem, so like the motors and the sensors, as well as configure the motor settings. So if you're using like a Falcon or a Talon motor controller, they have a lot of settings that you would have to put into them, and this is where you would do that. Then we have a loop variable, and this contains all the actions that happen during whenever the subsystem loops. So it has an onStart method that's called once whenever the subsystem is started. And this is where you would reset variables or reset the system state of the subsystem. Then we have an onLoop method, and this is where you would update the status of the system and usually kind of check the sensors and see if they've seen anything new recently. Then the onStop method is whenever like the robot gets disabled, or maybe even if your thread crashes, you would have a stop motor method that stops all the motors from moving, and that would also stop the thread at the end. You want to make sure that you stop the motors, because then say your robot gets disabled and your motors are still moving, that's bad. Then all of these subsystems have getters and setter methods, and this is a way of safely interacting with the subsystem. So say a driver wants to input a command to the subsystem and get it to do something, it would be through getters and setters. This is kind of like a safety thing, so that we never let the motor speed be public, so that if it is, then you might accidentally break something in the mechanism by turning on the motor at a bad time. So always make the motor speed setter private. Now, each subsystem does extend an abstract class, or kind of like a blueprint of all the methods it needs to contain. So I'm going to go over those now. The first one is the getInstance method, and this is used because we don't want to have more than one instance of a subsystem. So like our robot does not have two drive bases. And this is a way of also interacting between subsystems, so that if we want to kind of modify or make the drive base do something outside of it, then we would do the getInstance method. The next is the register enable loops method. And this is what the subsystem manager uses to add the subsystem to the looper. It's kind of in the robot.java class, you'll see at the very top, we'll have a register enable loops method call. And this is how we do that. The loop has to be a defined variable, and you'll see that it's usually named imLoop. And this will make more sense by actually looking in the program. Next, we have the stop method. This is kind of important because it's called whenever the robot is disabled. And this should stop all motors or kind of reset all the sensors and make the robot kind of prepare to be turned off. Next, we have the zero sensors method. And this is somewhat periodically called, or not periodically called by the subsystem manager, but it's a good way to zero sensors whenever the match starts. So say you have a gyro on board, gyros do kind of tend to slowly drift away from the start point, so you can zero your gyro at the start of the match. Then we have the output to smart dashboard method, and this is pretty useful because it's called somewhat periodically, but not every single iteration, and that would to prevent from over inputting data into the smart dashboard. And this is used to output things like motor speeds, sensor states, or even the state of the subsystem. And this is helpful because then the driver can look at their driver station laptop and kind of see what's going on, or say you want to troubleshoot something, you can know exactly what the program thinks that sensor says. Now this is a pretty heavy slide, but if you want to convert a simple subsystem into a state machine subsystem, this is how you do that. So for a state machine, it has two enums, a system state and a wanted state. Now the system state are the actual state of the robot, like what it's currently doing. then the wanted state is what the driver wants the system to eventually do. So the job of the state machine is to get the system state to eventually become the wanted state. So in order to actually set the system to what you want it to do, you would use a set wanted state method. Now, for the state machine, it's basically made up of a switch case statement, and you'll see this contained in the on loop method. So what it's doing is continuously looping this switch case statement and switching between the different system states. Now, for each system state, we have a handle method, and this is what returns the new system state based on what the driver set the wanted state to be. Now, to figure out to convert between the wanted state to the system state, you'll see many times we have a switch case statement. The handle method is also used to do whatever the system state does. So say we have a shooting system state. This would contain the code to actually have like the flywheel shoot. Then also to keep in mind is that whenever your robot is disabled and then enabled again, you want to sometime reset the system state and the wanted state because you don't want it to just continue what it was doing whenever it was turned off and surprise the driver. So usually when you reset the wanted state, it can be whatever you want the subsystem to do whenever it's enabled. And then the system state will usually be reset to something like idle, or in the case of a turret or a lift, homing. Now I'm going to go over examples of the different states. So this is kind of the difference between the naming conventions of a wanted state and a system state. So this is kind of for a shooter mechanism. We have a want idle state, a want home, or a want shoot. Okay, so the want idle is converted to just idle. The want home is converted to homing. But say we want to shoot. First, before we shoot, we have to spin the flywheel up to speed. So we would have a system state of spinning up and then a ready to shoot system state. And this kind of takes practice, and it's very specific to the actual robot that you have, but you'll eventually get used to it. Now I'm going to talk about the state machine classes and how they're set up. So the state machine combines multiple subsystems to form one mechanism. So this is the example I've been using, are that if you have a shooter, then the shooter would contain, say, like a flywheel, a turret, or a hood. And this greatly simplifies robot control. So whenever the driver says, shoot robot, they don't have to individually say, okay, spin the flywheel up, track the target, aim the hood, aim the turret, and feed the balls. They just say, shoot. And it's pretty easy to control by doing this. This also makes automation faster because when done correctly, automation is much faster than manual driving because the driver does have a reflex time and the robot doesn't really have that, so it's much faster. State machines do have a very similar structure to a subsystem, except in each handle method, you'll actually set the wanted state of the child subsystems. And you'll see this if you look through our 2020 program, especially for our shooter. You'll see it setting the state of like the flywheel or the turret or the hood. Next, this is the last thing I'm going to be talking about, is to give you an idea of how we tuned our shooter. So our shooter, if you don't know, it had a turret that controlled the side-to-side angle and a hood that controlled the vertical angle, as well as a flywheel that we can change the speed of the ball exiting out. So that's 3 variables. It's very hard to line up 3 variables to one target. So for our shooter flywheel speed, it increased based on the distance from the target, so that if we're very close range, we're not smacking the ball into the target. So first we found the min speed based on our minimum shooting range. So we just scooted the robot to as close as it could possibly, the limelight could see the target, and we found the minimum speed that the ball could come out. Then we found our maximum shooting range by setting the flywheel to max speed and finding the maximum range that we could shoot and actually make it into the goal. Then from these 2 points, we just found a linear line, and then based on the distance the robot was away from the target, we would change the shooter speed. Now we also had a tuning mode that was activated by the dashboard before the robot was enabled. So we only really tuned the hood maybe like 3 times, because once we tuned it, it was pretty set in stone. It was pretty good. And the tuning mode enables the manual hood adjustment. So first we would have the robot, we would put it at different distances from the target. Then we would move the hood manually until we found a good angle for the ball to consistently go into the target. Then, once we found that key angle, we would save it into a CSV file, kind of like an Excel spreadsheet stored on the RoboRio. And for each hood angle, we would record the angle, the flywheel speed, the angle of the target, and the time. And then eventually we would have like 10 or 12 points of different angles and different distances. Then we would export this file through what's called SSH. So then once we have an Excel spreadsheet of the angles and distances, I wrote a Java program that converts this data from the Excel spreadsheet into a literal Java class in the robot program. And you'll be able to see this in our, I think, a shooter tuning folder in our program. And you can see it'll say the date and the location that we actually tuned the hood. So it's kind of cool to see that. So thanks. Also remember, if you have any questions, just ask. Okay, thanks.